Let us do another example showing that the set is countable. This time we will look at counting a set of finite strings. So for example, first we could count all the finite strings made out of letters A and B. So remember, we denote such a set as AB star. The way we are going to do it is to count strings in order of increasing length. So first we'll count strings of length 0, then of length 1, of length 2, and so on and so forth. The reason we do it this way is so that at any point in time, we would count all strings, all finitely many strings of a certain kind before moving on to kind of the next stage, the next epoch. There is only one string of length 0. This is an empty string lambda. And let's say we map it to number 1. Here the formula will be a little simpler if we start with 1 rather than 0. Then let's count string of length 1, and there are two of them, A and B. Let's say A is a number 2 and B is a number 3. Strings of length 4, there are 4 of them, A, B, 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 B. So let's make them 4, 5, 6, and 7, and so on. So now, how do we turn this process into a bijection? You could already see that this process does assign every string a number. So every number gets a string, every string gets a number, and this pairing is such that every string only gets one number, every number corresponds to only one string. But let's say a few more things about it. So the number that we are going to assign to each string will be composed of a sum of two numbers. First, we will say how many strings have the length smaller than the one that we are trying to get a number for. So for example, if we are looking at a string AB, which has length 2, there are 3 strings that are shorter than string AB. The second part of the sum will be the actual index of this string among the string of the same length. So if we order them as AA being first string of length 2, AB being second, BA third, and BB fourth, again we just looking at a string of length 2, then the string AB will be second, and overall the function, our bijection, will give the string AB the number 5. So note that we couldn't just count string in dictionary order. If we would count empty string, then A, and so on, we would never even get to B. This is why we have to look at shorter string before longer strings. This is the same reason why with counting integers, we couldn't count all natural numbers, positive integers first, and then count all negative numbers, and we had to alternate between the two. However, dictionary order is very useful for counting strings of the same length. It gives us a very natural way to assign a number to every string when we are just looking at string of the same length. And this is very common thing to do again in computer science, to use a dictionary order, or in this case, you may hear it being called lexicographic order, to arrange a string of the same length from, let's say, AAA to BBB, or AAA to ZZZ, depending which alphabet you are starting with. So here's how you could get the actual formula for that bijection. If we look at strings of length n, there are 2 to the n such strings. And also we could show that there are 2 to the n minus 1 strings of smaller length. And we will prove this formula later. Then let me not put it on the slide, but you could derive it yourself. There is a way to make a formula which will take a string and will assign number between 1 and 2 to the n to that string, which will be its index among strings of the same length. This formula will give number 1 to AAA, number 2 to the N, to the number BBB, and so on. So now, given a string x, we assign to it a number 2 to the length of x minus 1, plus the index of x among the strings of the same length, and you could check yourself that this is a bijection. So now, say that rather than working with strings over A, B, which is kind of a strange alphabet, we want to work with binary strings, strings over zeros and ones. But we already had pretty much done all the work, and it's very easy to either convert our previous proof to replace A's with 0 and B's with 1s, and then have everything else the same, or just use the proof sort of as a black box in order to prove that the set of all strings over 0 and 1, all binary strings, is countable. So this is how we can do it. Let's define a new function, call it g, which will convert a string over zeros and ones to a string over A's and B's by replacing every 0 in that string with A and every 1 with a B. For example, a string 0010 will become AABA. So now, in order to get a bijection between binary strings and natural numbers, it's enough to compose those two functions, the function that's a bijection from strings over A, B's to natural numbers, and the function that converts a binary string into a string of A's and B's. And composition of two bijections is also a bijection, so that will give us a bijection.